Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about feature generation. And actually different methods for dimension reduction and actually generate new features from our input samples. Okay, and we want to talk about linear transformation. Okay, so the goal in this session and some other sessions, the goal is to generate features via linear transforms of the input samples in order to pack information. So our goal is to pack information in lower space in terms of dimensionality. So we want to actually remove information redundancy in data. So this is the goal. Okay, for this end we should first be familiar with basis vectors and maybe basis images or basis matrices. Okay, let's say our samples, for better intuition about our goal, let's say we have some data. So generally we know that from previous sessions that we want to have lower dimensions, especially if we can reduce the dimension without losing information. It is really great, because when we are in high dimension space, then we are probably very prone to overfitting, and so because we have cares of dimensionality in high dimensions and so on. So we want to stay in low dimensional space. So let's say we have some data like this. In this case, we know that just let's say for describing each of data, you need to have a 2D vector, okay, for describing each of these data. Let's say this is ith data. Okay, but as you could see, all of these data are on the same line. So if we project all of these data on this line, we actually end up with a new basis. So I call this new axis x3 prime, and in x2 prime we have our data, and we actually do not lose any information in here. And now for describing each data in here, we just need to have one component. So this is great. This is kind of dimensionality reduction. We are in 2D space, now we are in 1D space. Okay, so this is the goal of this session, to learn how to do this kind of transformations. Okay, so let's say our samples have n dimension. So in here we have n-dimensional vector, and we want to create a linear transform that transform this vector into another vector. We call that y with a linear transformation. So we know that linear transformation is described by matrix times our vector, and this H means Hermitian operation. It is not so it means actually complex conjugation of the matrix. If all of the data are real, then for real data it means that just A transpose X. So it is not very important. You don't need to actually be confused about this H. You just you can just suppose that it is transpose. Okay, and so we want to extract, actually our goal is to find the transformation. So we want to find A, because A create this transformation. So in this example, X is this vector and Y is this vector. Okay, actually Y is this vector and this one. Okay, but we just remove that because we don't have any component on that. Okay, anyways, and so A matrix, we assume that it is unitary matrix. Also, when we say unitary matrix, it means that A Hermitian A is equal to identity. But in real case, if A is real, then it means that A transpose A is equal to identity, or in other words, A transpose is equal to A inverse. So something like that. Okay. Okay. Now we know that A has different columns, and so because A is unitary matrix, using this property of the A matrix, we can say that from this and this, X is equal to AY. So we can expand it to sum of YI AI, in which AIs are the columns of A matrix. So we call this AI basis vector. So as you could see, Y is actually projection of X onto these basis vectors. So Y y's are projection of x onto these basis vectors, and then we get x from here. In other words, we could prove that the inner product of aj and x, which is aj Hermitian x, is equal to yj. So this is the meaning of projection. Okay. Actually, you may note that in here our data is one-dimensional data. What if our data is 2D? In the case of 2D, like maybe you have an image as your input data, so your data is like matrix. Maybe it has n columns and n rows, so it is n by n. So one way is to actually convert it to a vector by putting the rows, stacking them together, and create n2 n squared by one vector. But after creating this vector, then your A matrix related to this n squared dimension is n squared times n squared. Then the operation of transformation will be of the order of n quadratic, which is not very efficient. So there are other methods to use when we have images or 2D inputs, but for now we just use the basis vectors and we assume that we convert 2D things into just vectors. So now we could talk about an important transformation, Carhonen-Loewy, I think, and actually it is slightly different from PCA, but we can say that they are the same in our context. So or PCA, or principal component analysis. Okay, so we mentioned that we want to avoid information redundancies. What does it mean? It means that we want to uncorrelate, we actually want to transform the features to have uncorrelated features. Okay, so in this case we have a linear relationship between these two axes. So we have some correlation between these two axes, but if we convert them to these two bases, let's call them x'1 and x'2, then these two axes have no correlation. So we want to actually obtain a transform that data after the transformations are uncorrelated. So what does it mean? It means that the expectation of yi, yj is 0 for any I is not j. So this means that we want to have uncorrelated data after transformation, and we know that we want to have this transformation. And instead of Hermitian, I just put transpose because we work with real data, so they don't have complex or imaginary parts. Okay, and let's write the correlation matrix in here. We know that the correlation matrix is y transpose, so if we replace y with A transpose X, we end up with A transpose X transpose A. So it means that A is constant, so we have expected value of X transpose, which is the correlation matrix of X and times A. Okay, we know that Rx is symmetric because it is correlation matrix of real data. So eigenvectors of this matrix are orthogonal, actually mutually orthogonal. So if A is chosen so that its columns are the orthogonal eigenvectors of AI, then Ry is diagonal. So it is when Ry is diagonal, it means that this condition satisfied. So actually this is one way to create A. So for choosing A, we just need to choose the column of A so that its column are orthogonal to eigenvectors of R of X. So this is called KL transform or PCA. Okay, let's see some important properties to gain some insights about this. We know that X is equal to yi ai, and we know that yi is equal to ai transpose X. So now let's say we just throw some dimensions away and we create an X hat which is the approximation of X, but instead of n minus 1 in here, we just use a lower number than n. So this means that we want to reduce the dimension, and now we want to approximate the projection with the real data. So in this case now, if we want to know that how much we have error, we could actually derive MSE error, which is the expected value of the difference between X and its projection. So if you calculate this, you will end up with I from M to n minus 1 AI transpose expected value of X transpose AI, which is in fact the sum of m to n minus 1 of eigenvalues of Rx. So so this is MSE, or mean squared error. So if we want to minimize mean squared error, we could choose a column of A such that they are eigenvectors corresponding to the m largest eigenvalues of R of x. So in this case, the MSE error would be minimized. So for having better insight, it is very great to see what does it mean on a plot. It says that if you have 2D data and your data is something like this, then the eigenvalues, the eigenvectors of your correlation matrix is like this. One of them is in this direction and another is in this direction. So let's say that we normalize them to have unit norm, and because in here we have in this direction we have larger variance, or we could say that we have larger eigenvalues in here, and so we know that lambda 1 is greater than lambda 2. So PCA says that if you want to reduce the dimension of your data, you could let's say we want to reduce from 2 dimension to 1 dimension. You could choose the direction that data have maximum variance in that direction. So in this case, if you want to choose one direction to project your all of your data into that direction, you should choose this direction. Okay, so this is all of what PCA says, and but clearly you see that if you choose this direction, then all of the data will be mixed, so you will have lots of information loss in here. But if you project this data on this line, then your information is still okay and it is not lost. But you should just note that PCA does not work always very well, because it is actually blind to the labels of the classes. So let's say you have a classification problem and your data is something like this. So in this case, if you apply PCA, PCA does not have nothing to do with the labels. So it tries to find a direction that all values have the maximum variance. So the PCA direction for projection is this direction. And if you project all of your data on this direction, then you will end up with probably something like this, and so all of your data will be mixed from two classes, and so your algorithm performance would be very poor. But we know that in this case actually the second direction of PCA is the best direction to project the data. So just note that always PCA for dimension reduction does not work very well. So actually in this case LDA works perfect. And yeah, that's it. So you should note that PCA is a method for dimension reduction, so you could visualize the data in 2D with using PCA by just reduce your dimension to 2D or 3D, then visualize them. And actually you could use PCA to reduce the dimension to increase maybe your performance of your algorithm in some cases. In some other cases maybe your results gets worse, so you should try that. And so I hope that you get that now, why we call that PCA, because it means that principal component analysis. So principal component, as we mentioned, that they are principal components that are in the direction of the maximum variance of the data. So if we had three-dimensional space, then PCA would recommend us at first the direction that has the maximum variance, then the second variance ranking, and then the least variance as the projection recommendation. Okay, so that's it for the theory of PCA. Now you could use actual PCA in Scalar very easily. So Scalar PCA in here. Okay, you could see that you could define your PCA with your desired number of components that you want to have. Then you just fit your PCA. Then you could use your PCA to transform your training data or test data. So in here I want to show you an example for actually putting all that we learned together in here and using PCA. Okay, first we import pandas and we want to work with iris dataset. So we download that and read that as CSV with pandas. Then for pre-processing we use a standard scalar that we learned about that in the previous session. So we just transform our data with standard scalar. So actually we make our data zero mean and unit variance. After that we use PCA. So we define PCA with two components. So we currently our feature vectors have 1, 2, 3, 4 dimensions, and we want to reduce that dimension to 2. So we transform the data with this PCA object, and so we call them principal component 1 and principal component 2. Then Now we want to just visualize the data to see the shape of them after the transformation of PCA in this space. So if we plot the data after applying PCA, we will see that we have something like this. So in here we could say that PCA did very well in here. So if we apply a classifier in here, it actually probably get a very good performance. And actually you should know that when you use PCA, your actual speed of learning algorithm probably will increase so much. So if you have an SVM that you want to train on your feature vector is maybe 10,000, and you have 10,000 number of samples from this 10,000 dimension feature vector, then probably you will end up with lots of time consumption for just training an SVM. But if you use PCA and reduce your 10,000 dimensions to maybe just 100 or 200 dimensions, then probably your learning algorithm maybe performs better, and its speed actually definitely speed up. So using PCA is actually is a really good idea at the first sight, at least, to try PCA. Okay, yeah, that's it for this session. There are some other methods for feature dimension reduction. As we could see in here, PCA is using linear transformation. Actually, there are other methods that use nonlinear transformation, and also some of them also use linear transformation, but they have little difference with PCA. So we will discuss them in the next session. Hope to see you in the next session. Bye.